Okay.
I like that one though.
Okay. Okay. So, ladies and gentlemen, um, let us return to our purpose. We're going to be examining here some aspects of nonlinearity that are going to be prominent with this model. And to do that, we need to put into place a few more components, and most specifically, the key component that's going to add some nonlinearity in. But my purpose is also to show you some of the feel for building systems like this. And I'm going to introduce a new type of construct, which is going to be an auxiliary variable. These are variables that are convenience variables. I noted them earlier, which are going to afford us an easy way to kind of label some common quantities within the model. So I would like you to take your model, and now I'd like to go create an auxiliary variable. It'll be called a dynamic variable here from the palette, and here it is, dynamic variable, and we're going to drag it up here to the top, and it's going to be called total population. Okay. Now in this case, the total population turns out to be static, but in general it'll be an open population. So we're going to create this variable to reflect that. It will afford us some flexibility. So what did I do? I went up and I dragged in a dynamic variable and I called it total population. Okay, and now this total population is going to depend on what? Can anyone tell me on what the formula for this will depend? Good? Good. That's exactly right. So we need to, in order to have it depend on those things, we need to indicate at a high level that it does depend on these things. Again, a diagrammatic notation of system dynamics that enjoys many virtues to recommend it. By visually seeing this connection, you know that, okay, it depends on that. Even if you don't want to go in to look at all the vagaries of exactly how it depends on it, you can see, oh, it does. And that allows us to parse these models with somewhat more transparency than would otherwise be the case. Okay, so what I'm doing is I'm linking these up, and I'm going to frob these so that they head in more pleasurable directions. Okay, so here we go. Just you can frob them at this center point, or you can double click on some of these. I guess these you can't double click on to sort of bend them and contort them in ways. Okay, that's great. So we have total population, and it is now linked to each of these stocks. That's great. And ladies and gentlemen, I'd like you here to place into this population, place into this a formula. What will this formula be? Can anyone spell it out? Susceptible plus, and I'm typing this out, but I would suggest that you do like this and do control space and actually let it fill it out for you, so you don't have to type it in the same way. Okay. Okay. Build early, build often. So here we have total population. That's great. Now we're going to have a variable that's going to reflect the prevalence of infection. Okay. Okay. So here we go. We're going to drag another variable called prevalence.
Is that line across the screen?
Yeah, the line that's up there, it's a great question. And I take it you're referring to this line? Yeah, it's there particularly for when you're building an agent-based model. If you go to the left-hand side there's kind of this origin, and that will provide a reference point for understanding when you place something visually that's going to be part of an agent, where it will lie relative to their logical position. So it's not something we have to worry about here, but it does carry meaning. It's a little bit of an artifact that it appears in this particular model, since we won't require recourse to it. Yeah. Okay, so ladies and gentlemen, on what will prevalence be? What will dictate prevalence? On what will it depend? Mm-hmm.
Infective.
Good.
Divided by
Mm-hmm.
susceptible, I think.
Prevalence will be infective divided by the population as a whole here. Although I know what you're saying. I mean, it can be defined. Incidence can be defined incidence could be defined relative to population at risk. In this case, we're going to be computing fractional prevalence, the number of people with the bug over all people in the population. So we're going to have prevalence. The formula for it will be dictated by infective divided by total population. Probably I should have called it with a lowercase p to be consistent, but okay, that's okay. Maybe I'll change its name to lowercase p prevalence, just to be consistent. Okay, great. Okay, we're getting close to the to a key approximation. Okay, now, ladies and gentlemen, this is going to be a notable finesse associated with an aggregate model, and it is something that is a approximation that's very common, dates back approximately a century, but as Ross noted, it has its limitations. So what I'm going to put into place is another dynamic variable called mean infectious contacts per susceptible. Okay. There we go. Okay, it's Kurt. Green is the color. Okay.
You didn't say sector 1.
Yeah, sector 2.
Oh, 2.
Yeah. No, actually, she's technically sector 3. She's beyond the edge. Yeah. Okay. Mean infectious contacts per susceptible. Okay. And to support this, and I should have actually done this first, we're going to have mean. We're going to have mean contact contact rate. Okay, mean contact rate. This is going to be a rate, people per unit time.
Is that mean parameter?
Per person. Yeah, it's a parameter. Yeah, mean contact rate. Sorry, it's a parameter.
I'm sorry, can I see the other one, please? The one that says contact.
Yeah, mean
Thank you.
infectious contacts per susceptible. Okay. So the idea here, and this will this may raise heebie-jeebies, perhaps cause worries, or otherwise cause displeasure on Ross's part. So here we're going to have a mean infectious contacts per susceptible be the result of multiplying the prevalence by the mean contact rate. And I'm going to talk about assumptions built into this, and in some cases why it might be a poor assumption, in some cases why it might be a suitable assumption. But we're going to put that into place right now. And this is associated with what Ross did term as the principle of random mixing. So here we're going to assume, ladies and gentlemen, that we have some mean contact rate, and the values for this are going to be 12 contacts per person per unit time, okay, per day. And that would again be the sort of thing where we might have some empirical data. If it were sexual contacts, or the things might be remembered better. If it were contacts that are sufficient for airborne infection, it might be the sort of thing that are addressed by modern digital epidemiology systems, such as our IEPI system, on which Kurt and others work. Or for other types of contacts like bloodborne infection, it might be assessed through analysis of reports of needle sharing, for example. We're going to talk soon enough about where data for that sort of thing might come from, but that's a parameter value. It's an assumption we're going to have in the model. And the value of mean infectious contacts per susceptible per day is going to be the mean contact rate times the prevalence. So the idea is if you have contact on general with 12 people per day, and if the prevalence in the whole population is 50%, you'll have contact on average with 6 people per day who are infective, okay? So we're going to call it mean contact rate times prevalence. That's going to be the formula for mean infectious contacts per susceptible, okay? Okay. Great. Okay, and next, we're going to actually modify something we put in place before, to wit, the incidence rate. Okay? And the incidence rate is in fact going to be a multiplication of this mean infectious contacts by susceptible with one more parameter. And this new parameter is going to be a parameter that's going to be I'm going to say probability of transmission per discordant contact. Now you may hew to a briefer name, but I'm trying to be evocative and clear in my names, trying to indicate clear intentions. Probability of transmission per discordant contact. So that's the question. If this were needle-borne infection, it would be what's the chance that if I share needles with you and you're HIV positive, for example, or for Hep C, HCV positive, what's the chance that I'll develop that illness from sharing a needle, from a needle sharing contact? Or what's the chance that I'll develop an STI from having sexual contact on a per contact basis? This is going to be the probability of transmission per contact between a susceptible and an infective. And the value, ladies and gentlemen, will be 0.01. Okay. Now,
Wait,
yes,
you made that a parameter.
I made it a parameter.
Oh, mean contact rate times.
Yeah.
What
Yeah.
does that mean again, a parameter versus the dynamic?
Okay, so it's a great question. A parameter encodes an assumption about the model, an explicit numeric assumption. Actually, it's not quite true that it has to be numeric. Ross and Matt and others will be interested to know there's also a thing called dynamic parameters, which basically provides a rule that you can specify as a parameter for in certain contexts. But basically, it's a quantitative assumption about the model that you will specify in this case in the experiment. Okay, whereas a dynamic variable is something that's calculated within the model, and it's typically an endogenous quantity. In short, the parameters encode exogenous quantities which are represented, but which we are telling to the model, and the dynamic variables represent endogenous quantities that are generated by or otherwise calculated by, produced by, or emerge as emergent properties of the model. So that's the distinction. Does that help at all?
Oh, yes.
Okay. Okay. So ladies and gentlemen, on what does incidence rate depend here? It'll depend on two things. The incidence rate for a given susceptible, what's the chance that they're going to get infective in a given day? It'll be the result of two things. First of all, it will depend on how many contacts with an infective they have per day. So it's going to depend on this guy here, the mean infectious contacts per susceptible. To have been clear, we should have called it contacts per day per susceptible, but it's a contact rate. Okay. So it depends on that, and it also depends on this parameter. For each of those contacts, what's the probability of transmission? And in the final little component here, ladies and gentlemen, for the incidence rate, we're going to now replace this value of 0.10 that we've been using and replace it instead with this value times that value. So this probability, and I would suggest you use control space to fill it out, but I'm going to write it out in long form here.
What was the probability of transmission, the number?
1%. Transmission per discordant contact. Yeah. Discordant contact. And then it's going to be by mean infectious contacts per susceptible. Okay.
So
Yeah. Uh-huh.
you basically have to make these connections in two places. One is on the model itself by building in the links, and the other is
Right.
in the definition of each.
That's right. Building in the links gives you a high-level understanding on which things does it depend.
Yeah.
But you have to say, and that's kind of what a causal loop diagram gives, right? It's like this depends on these other things. But to make it precise, you need to give a formula. To make it simulatable, you need to give it a formula, because just knowing on what it depends doesn't tell how it depends. So I just made this guy times that guy, which is a time-honored and time-faulted sort of approximation. Okay. Okay. It's actually fairly robust. Okay, Kurt's working with someone. Matt, any chance you could help out here? That'd be great. Okay, I think we're done with the next stage here, which is Kurt didn't like my term for it, but it's okay. Okay. So who would like me to repeat something here? Right here, Gina.
I missed several connections I haven't still made.
Okay.
But
Okay.
Not the only one.
Okay.
My question for you though is, I was supposed to make this a
Okay.
parameter
S-
and I made it a dynamic variable. Is there a way to just
You-
change the
You
type?
gotta delete it and create it again.
So if I do that, and I've got, I have this one connection, does it delete the connection?
Okay.
So I
So
can leave the connection.
because some people may need a bit of extra time here, I'm going to go back and rehearse everything I've done since in terms of adding these variables, just so you can walk through, okay? So the first one I added was total population. Total population was given by the sum of each of the stocks, susceptible plus effective plus this one. This total population. The second thing I added was prevalence. Prevalence was equal to the number infective divided by the total population. Thirdly, conceptually I added mean contact rate, and I added a dynamic variable called mean infectious contacts per susceptible. And this was given by the mean contact rate times the prevalence. The next thing I added was incidence rate. Well, I added this thing here, which is probability of transmission per discordant contact. And I added incidence rate, which is this parameter times this one here. Would anyone like me to show any of these again? Would anyone like me to go, Kurt?
No,
Gina,
I
or
was
question? Yeah.
Responding to you.
Yeah.
What is the mean contact rate?
It is 12. 12 per day. Okay, who else would like me to show one of these? Would anyone like me to show one of these? Okay.
The mean infectious contact
Yes.
per susceptible, so that is defined.
Mean contact rate. Suppose I have contact with 12 people per day and 50% of the whole population is infected. Then I would have, on average, contacts with 12 infected people per day. So 12 people with anyone, 50% of the whole population is infected. I'm approximating, okay, I on average have contact with 6, that is 12 times 0.5 people per day who are infective. So it's mean contact rate times prevalence. You got that? Okay, who else would like to see additional ones? Anyone? Okay. Okay, who would like Krugerian help? Green is the color, okay.
When he was the professor in
Yeah.
the class, we called it professorial help.
Okay,
You should have prevalence.
yep.
Sign up.
Prevalence is number infective divided by the total population. Okay, who else would like, I'd be glad to do show and tell for all of this. Who else would like one? Okay, are people ready to run this? Okay, you ready to run it? Okay, okay, let's run it. But Kurt stands in the wings. Okay, okay, okay. So, ladies and gentlemen, let us calculate. Okay, so we're going to run it out here, and oh, look at that. There's something that's missing. There's something that's missing. We didn't specify something. Okay, what's going on here? Mean infectious contacts per susceptible is 0. Prevalence is 0. Infective is 0. No one started infective. Okay, so guess how many people stay infective?
That same number started.
Yeah, there ain't nobody to infect them. So, ladies and gentlemen, let's start with one person infective, shall we not? Actually, I'm going to cut something short because time is running short. I'd like to start with 470 people infected. Okay. Sorry, I'm doing this for a reason. Okay. So let's make it a value like 470. Is that okay? Okay, let's run this. Let's let it run. Okay. There we go. What happened, ladies and gentlemen? What's happened? Can anyone describe? What happened as we ran this out? Not everyone got infected. Did anyone get infected? Yes, quite a number actually got infected. Over 50,000 of them, but not everyone, right? Okay, so that's good. Let's try to parse out what happened here. If we were to go and let's start running this out from the. Okay, we have to be careful because this runs so quickly. I'm gonna go back to this main page and I'm gonna say run, and I'm gonna run this forward and I'm gonna plot out infective here, and I'm gonna speed it up a little bit. Okay, so it's rising. And it's rising. What does it mean that infectives is rising? What's greater than what? Kurt? Sector 3. Sorry? Incidence is greater than recovery. More people are getting infected than are recovering, okay? And then now it's flattening out. That's an indication that those two are equal at that point. Let's continue to run this, okay? Now it's going down, so the number infective is going down. Why is it going down so rapidly here? Why is it dropping very rapidly, the number of people who are infective? Well, give me one reason. Well, people are recovering, right? But another reason is, how many people are getting infected? Well, the fewer infectives there are, the lower the prevalence, the lower the infectious contacts that are occurring, the lower the incidence rate, and the fewer people yet are getting infective, right? So, in fact, the number infective here is dropping very rapidly, not only because they're recovering, because very few people are getting increasingly few people are getting infected in the first place. So, there's kind of a positive feedback there that is the flip side of the positive feedback seen at the beginning time. At the beginning time, we had quite a few people getting infected because what was going on? Can anyone tell me the vicious cycle, the positive feedback that's occurring initially? What was going on in that initial phase? Kurt? What was going on in the initial phase? What's the positive feedback in the very initial phase? I'll run this again so you could see it. Here's the number infective. Why is it rising so darn quickly? Good. A lot of people susceptible. Those people get susceptible. They get infected. And the more infectives there are, the more contacts there are with infectives, and the more there's a higher chance of getting infected for a given remaining susceptible, and therefore it rises yet further and further. And so it's rising very quickly. This positive feedback is dominating initially. Eventually, however, as you run it forward, there's limits in the number of susceptibles. So this is going to be drained down, and as you drain that down, there's going to be fewer people who are becoming incident, fewer people who are developing the infection. And as that's dropping, there's the rate of incidence is going to be increasingly close to the rate of recovery. And this is why this flattens out. I'll be with you just a sec. And as it flattens out, that's when the incidence equals the recovery. And, or put it at an individual level, each person is going to infect exactly one person to replace them when they recover. So at an individual level, I'm going to be replaced by exactly one person that I infect. So it's kind of, I'm not spreading the infection, I'm just replacing myself. Early on, I'm spreading the infection. I might infect two people, each of them infect two. So early on, it is spreading very quickly in this positive feedback. It's going faster and faster upwards. 2 becomes 4, becomes 8, becomes 16. Now, when it reaches this, as it goes on though, there are fewer and fewer susceptibles. It becomes harder and harder to spread it because more and more of my contact as an infective is with people who are immune or are currently infected. There's fewer and fewer susceptibles until the point where I'm very inefficient. I'm just replacing myself. And then the number of infectives starts to drop. And as the number of infectives starts to drop, it drops faster and faster and faster because there's more and more people there's more people recovering here. I mean, lots of people recovering over time and fewer people getting infected because with fewer infectives, there are fewer contacts, lower risk of infection, and therefore less incidence. So it's dropping faster and faster due to both high recovery and low incidence. And then it goes down to a very low level where it's very inefficient to spread. It's so inefficient to spread, it essentially dies out, the infection in the population, and lots of people are left still susceptible in this case. So question?
Yeah. So on this model, you have like, mine when I stopped it, I had like 1.859
Indeed.
infected people.
Indeed.
You can't have that in real life.
Indeed. So I was going to talk with you about this. So this is a very interesting case. And it's a fascinating case of this. We recently had a paper published in SDIs, I think it appeared, where we looked at this phenomenon because there was another prominent model out, one from Dave Fissman's group at the University of Toronto, which was look at antimicrobial resistance, and particularly for gonorrhea, which is an infection where it's known to exhibit substantial amounts of antimicrobial existence in many locales worldwide. And one of the things that they provocatively suggested was that that actually can be deleterious to focus on high-risk groups with antimicrobial resistance, it being a possibility because it tends to lead, they argued, to a faster level of development of antimicrobial resistance. In other words, by focusing on the high-risk group, which is, as Ross and others know, a very common strategy to fight STIs that came out of modeling work in the 1980s by Heathcote in York, for models like these, in fact. David Fissman's group argued that actually in the presence of antimicrobial resistance, that's downright dangerous because it puts you at risk of developing even faster antimicrobial resistance. And their argument, it turns out, hinged, and this was a very interesting methodological point. So the first thing we did is we built an agent-based model to see with an agent-based model with realistic contact network structure, more realistic depiction of natural history of infection and of development of microbial resistance, whether this is likely to be an issue. And another feature of it that I was quite interested in was exactly what you're asking about, the quantized population, the fact that you don't have a millionth of a person infected with antimicrobial resistance. That at a biologic level, we're talking about a situation where really you need to have antimicrobial resistant bugs dominant in your gut or not, and you're not going to be having some mixture between them. And that's what I understand from my immunological colleagues anyway, who are experts in gonorrhea. In any case, we looked at this with an agent-based model, and we did not see the same phenomena arise. And so we said, okay, so what's going on here? Is it a matter of the network? No, it's not a matter of the network. And we basically pieced apart the situation. And what it turned out to be is exactly what you're asking about. That basically their model was assuming that in the presence of an intervention, that you can have you can have the infection rate of gonorrhea, the prevalence of gonorrhea reduced arbitrarily small, but have some small residual amount of it that is drug resistant. So you might have 10 to the minus sixth of a person being drug resistant. And then over time, inevitably, if you add 10 to the minus sixth of a person being drug resistant, it would grow to 10 to the minus 5, 10 to the minus 4, 10 to the minus 3. Over time, the antimicrobial resistance would spread from these fractional people and eventually come to dominate, 20 years out or what have you, 10 years out. And so we took a model like this and we imposed only quantized individuals, only individuals who are integer in number on their model. And we saw their effect disappeared. In fact, their effect hinged on the fact that you would have fractional people, in fact, very small fractions of people who could still be infected with antimicrobial resistance. And what you had to assume in the context of their model was a population of billions of randomly mixing people for you to see this development of antimicrobial resistance. Actually, I think it was tens of billions for it to be likely. And so you're absolutely right. This is a shortcoming of, I wouldn't say it's a fatal shortcoming, but it's an important one to be aware of these sort of models. The fact that you can get this. This model right now is positing that we have somewhere around about 5% of a person infected. Now, if you talk with people, there are people who say, we'll try to interpret that probabilistically. Well, what it's telling us is about 5 cases out of every 100, someone will be infected still at this time. And there are cases where probabilistic interpretations can be reasonably put to things like this. But in a case of a nonlinear model, it doesn't work well. It does not that argument tends not to work very well at all, because the results of assuming some where there's one person infected and many where there's not infected, on average, don't average out to the same as assuming a 20th of a person infected. So you put your finger on something which is a concern. Now, in this case, it is not a concern that is likely to be a binding one. You're not operating in regions where that's critical. But for the Fissman paper with antimicrobial resistance, it was absolutely central, because basically you could not show the development of antimicrobial resistance in the long run as a result of arguing that it's the adverse results of focusing on high-risk groups without positing very fractional individuals infected. Here, it's just something you've got to be cautious about. And I guess this is one of the issues that comes up with system dynamics aggregate models. with aggregate models of this sort in general. There are approximations here. And if you're savvy to the approximations and very careful, you can sidestep a lot of issues and know when it's a problem and when it's not. But I will say that a lot of these things can be sidestepped directly with an individual-based model because you don't have to assume partial individuals. You could put in place mechanisms here, and I won't do it because it would distract us from our final hour here. But you could put in place mechanisms that would impose, you treat it as 0 or 1 person, and as soon as it goes below 1, you treat it as 0. Boom, done. But it takes a little bit of savviness, like your own, to recognize that that could be an issue. Okay? Yeah, great question. Okay, so ladies and gentlemen, we're closing in for the final components here of this little exercise. I'd like you to go to the palette, and I'd like you to extend a link betweenst recovered here and susceptible. Now, to do this, you're going to need to undergo a little bit of finessing. So I'd like you to put a link. Let me do this again. I'd like you to put a link that extends from recovered and immune. So I'm going to delete this, and I'm just rehearsing this to show to people. I'm going to drag it over here, and I'm going to put it so you can see that nice green dot. Green is for go. The flow, sorry. What am I saying? A flow. I'm sorry. Yeah. Okay. And we're going to call this waning. We're going to call it waning of immunity. Waning of immunity. Okay? That's great. Okay, now, we need to now put this, sorry, I disconnected it in a most unseemly fashion. Okay, out, black spot. Okay, there we go. Okay, great. So now we need to position this so it extends over to susceptibles. How are we going to do this? This is what I'd ask you to do. Double click in the middle of the link, so the middle of this segment of the link, not at the plumb at the center. And then that will allow you to actually have some extra flexibility with the link. So I'm going to ask you to sort of pull it like this. And depending on your measure of aesthetic sort of tolerance, you could shape it in any number of different ways. I'm going to shape it in the following way. I'm going to double click here. Come on. Oh, come on. Get over there. Here we go. Okay. Hey, no, why are you not? Okay. Okay. So be it. Okay, there we go. So I'm going to drag it like this, and I'm going to drag this guy down like this, and there we have a proper square link. But some of you may prefer different shapes. So how did I get that? How did I bend it? I double-clicked with a measure of ferocity at the end at those locations. Okay? Okay, great. So now, ladies and gentlemen, I'd like to put in place a final parameter that's called duration of immunity, or duration of immunity, immunity duration, immunity, yeah. Okay, and I'd like you to hitch it up to that newly to this new flow. Okay, there we go. There we go. Okay, hey, come on. Hey, don't give me that. Okay, there we go. Okay, what else must this flow depend on to be physical? There could be no one going down this flow unless, what? There's people in what stock? Recovered and immune. So we need a link from recovered and immune to waning of immunity also, reflecting that dependence. And this will be a first order delay. And the formula for that first order delay will come from what source, ladies and gentlemen? It'll come from none other than you. Okay, so tell me what formula to put in here if this is a first order delay. If I have a duration like this, and do you remember what I did? For a first order delay, what's the formula here? It's the value of the stock, and is it multiplied by or is it divided by the duration? It's actually divided. The longer the duration is, the slower the rate of people coming down. If it takes people 100 years to lose immunity, there'll be fewer people heading down there. For a given number of people here, it's going to require 2 days to lose immunity. Okay, so this flow has a formula associated with it that's given by this here. Okay, great. Okay. So, ladies and gentlemen, how do you think this will affect the situation? Riddle me that. Well, first of all, we need to set the duration of immunity. And for that, ladies and gentlemen, I'd like to set it to 275 days, no less. A good long time. 275. Now, why would you lose immunity? Well, there's many reasons. For gonorrhea, it's due to an outer membrane protein mutating, OPA types. For HIV, there's all sorts of mechanisms to allow it to mutate quickly. Of course, you're not getting reinfection there, clearance. For flu, it evolves very quickly as well, second only to HIV, I'm told by immunologists, in terms of its rate of evolution. So there are cases where effective immunity wanes. The immunity you built up last year doesn't hold for the next year's flu season for certain strain types, or your exposure to gonorrhea types will be not protective after a while due to changes in the types that are circulating. Okay, so waning of immunity, duration of immunity is 275 days, and the waning of immunity here has a formula associated with it of recovered and immune divided by duration of immunity. Okay, so ladies and gentlemen, how do you think this will change the situation? What do you think will happen? Okay, so we had a bug before. There was like a fire. It sprung up, it burned for a while, produced a large charcoal to the point where it couldn't burn any further, and it went out. It went down to arbitrarily low levels and just went extinct. Now we're not getting that situation anymore. So let's run this thing. Okay, now we get cycles, we get oscillations. Ladies and gentlemen, let us reason about these cycles. And unfortunately, the one of greatest interest down here for infectives is not so obvious. It's a little bit smaller here, so I'm tempted to break that out into a separate graph so we could see it with greater clarity. If any of you would like to do so, I will show it on my screen. You don't have to do it yourself, but what I'm going to do is to take this graph, I'm going to right-click on it and do copy, and then I'm going to click here and I'm going to do paste, and I'm going to just edit that second graph such that it omits those first two of the items, to wit, the number susceptible excuse me, the first and the last of the items. To wit, the number susceptible and the number recovered. I'm going to omit them because they crowd out the other visually. Okay, so now I'm going to run this again, and we'll be able to see with greater clarity exactly what's going on. There we go. Here's the number infected. So what's going on there? Why does it rise and fall and rise and fall? Well, ladies and gentlemen, where did we see a case? So before, what did we see? We saw a situation where number of infective rose and then declined and stayed low. Here, we see an oscillation. Oscillations are associated with what? Do you remember with causal loop diagrams? They're associated with delays in the context of a negative feedback. Yeah, so here, there is a decay, but there's a delay in associated with loss of immunity, and it actually leads open to this possibility of this cycle. This is sort of a secondary outbreak, as it were, a tertiary outbreak associated with peaks and troughs over time. So we have some initial outbreak, and let's reason about what's going on here. You can see the corresponding graphs up here. So I'm going to highlight this one here, the number susceptible. So what's going on here? The number of infectives rises. It's rising very, very quickly, ever faster here because of that vicious cycle, right? Infection begets infection. I infect 2 people. They infect 2 each to make 4. 4, 8, 16. It's multiplying very quickly, exponentially. But as it goes on, the number of susceptibles comes down to the point it's getting increasingly difficult for me to infect people before I recover. To the point where I infect exactly 1 person here at this peak, or where susceptible number of rate of infection equals rate of recovery. The stock is in balance. This stock here of infectives is in balance because the rate of this equals the rate of that, and people per unit time getting infected. And then it starts to decline. It declines faster and faster because as there are fewer infectives, there's fewer new infections, which means that the rate of recovery exceeds ever more the rate of incidence, and therefore the stock is dropping very, very quickly. And it drops, and it continues to drop. But you notice that as it's dropping, what's going on to the number of susceptibles? Is it continuing to drop? No, now it's starting to do what? To go rise. Why is it starting to rise? Well, there's a delay associated with things. They got infected, they were recovered, and now they're starting to come back to susceptible again. So it's starting to rise precisely because now people are starting to become susceptible. Why is it, even with this rise, that you still see a decline here? Well, sure, the number of susceptibles is rising, but the incidence is still less than the recovery. Why is it less? Well, there's fewer infectives over time, and there's not enough susceptibles to make up the gap. So the number of infectives is still dropping, even though this is rising. But that rise in the number of susceptibles eventually turns this around, and now you get the grounds for a second outbreak. The delays are critical there, folks. It takes time for this to build up enough susceptibles to really turn this around. And so it's declining because the incidence remains less than the recovery all through this time, and that allows the susceptibles to build up, and then boom, you have the grounds for another outbreak. And it declines in another outbreak. So here we have stocks and flows, these accumulations with resulting dynamics of infection that are dictated by delays associated with these stocks and flows, the rises and falls associated with these epidemiological quantities can be understood in stock and flow terms. And this is a very important point. I stand before you as someone who, as I said, applies ABMs to most projects, although often together with system dynamics, either in separate models or in the same model. And I personally find stock and flow parsing of a situation to be something extremely powerful. And if I have an ABM, I will often seek recourse to a summary at a stock and flow level of what's going on. Say number of new infections, number of people in different health states. Even if my primary tool for characterizing the processes is not a stock and flow model, I find it very, very helpful for understanding the dynamics that I see. And in fact, if you run ABMs, on an ongoing basis, like our group does, you will see exactly these sort of patterns writ large, and from model to model, or similar patterns which you can come to appreciate what's going on in a stock and flow sense. I'm not saying for all those models, far from it, are stocks and flows used as the mechanism to characterize the process, but they're used as the mechanism to understand what may be going on at a high level that can be very powerful. So understanding, ladies and gentlemen, stocks as accumulations and flows and the feedbacks that drive them can be really helpful for parsing what otherwise seems like a puzzling pattern into a sort of sensible understanding of what the underlying drivers are. But we're not done yet. We have just a short distance left to go, but a distance that will be rewarding, I believe. So, ladies and gentlemen, I'd like you now to put in place the final component of this model. And it will be a component that in fact involves aspects of care seeking and indeed of care delivery. So, ladies and gentlemen, I'd like you to put in place a parameter. It'll be a parameter here. We could have made it a stock and had dynamics associated with it, but I elected not to do so. And this stock will be called healthcare workers. Okay, healthcare workers. These could be nurses, public health nurses working in an STI clinic, individuals who are treating gonorrhea, for example, in an outbreak, what have you. I'd next like you to have a parameter that's called staff time per patient. Okay. This is going to relate to sort of healthcare service delivery. And then finally, one other parameter that's called time until seek care. Time until seek care. What we're going to be depicting here is a treatment-mediated infection. In other words, the treatment is required for recovery here. And this is an area where we've done a lot of modeling, both using stocks and flows, and found great theoretical insights, but also using agent-based models, and found highly consistent results, even with very textured assumptions concerning the care processes being delivered, natural recovery, and other components, and heterogeneity. Okay, so here we have we're going to have recovery delay depend on these three variables: staff time per patient, healthcare workers, and time until seek care. Okay? And then finally, this recovery delay will depend on one other thing, namely the number of infected people. The idea is that we're going to have infected people who are awaiting care. They need care to recover. They need to be treated to recover, and there's a waiting list. This is similar to a situation characterized in Britain by White et al. In the case of STI clinics in waiting times for treatment. So there's going to be a recovery delay. This recovery delay, ladies and gentlemen, will be a function, first of all, of the time until seek care. So again, I have staff time per patient. Maybe I'll go through and give these numbers. Staff time per patient will be 0.5 days. Healthcare workers initially will be 30. Time until seek care will be 5. Okay, 5 days. Okay. 5 days. So staff time per patient, 0.5. Healthcare workers, 30. Time until seek care, 5 days. Recovery delay here, we're going to give a formula for. What will it be? It will first be time until seek care. Remember, autocomplete is your friend. Control space will fill it in. Different possibilities, and you can choose it easily rather than typing it longhand as I am doing here. So we want to have a formula there, which is going to be given by that item plus, and I could break this out as a separate variable, but I'm just going to type it here for speed. It will be staff time per patient times infectives divided by the number of healthcare workers. So the idea here is per patient. Patient. Okay, that's what it is. Oops. Okay. There we go. Yeah. Okay. So the idea here is that each patient requires a certain amount of time per patient. Each healthcare worker requires a certain amount of time per patient. There's a certain number of infectives that have got to be treated, and there's a certain number of healthcare workers to treat them. So if you're last in the queue, this is the average time you're going to be waiting, sort of this amount of time. The amount of time given by, you've got all these people ahead of you, you've got this amount of time that's required to treat each of them, and this many people working with them, and therefore you're going to be you're going to have to wait a certain amount of time. Okay, so this should be infective, not infectives. Okay, so it's infective. Okay, so let's build early, build often. I know that's a handful. Do people want me to put that up on the screen? Yeah? Would that be desirable? Here we go. Okay. Let's copy this down. Okay, copy. Here we go. Paste. There you go. So, that's the formula for recovery delay. Time until seek care. That's the amount of time I need to go to seek care. If there's nobody ahead of me, this will be 0. The number of infectives will be 0. I'm the first patient, and I'll be seen in this amount of time. On the other hand, if there's 2 people ahead of me, each of them is going to require this amount of time to be seen, and they're going to have to be seen by a certain number of healthcare workers. If there's 30 people ahead of me, 30 healthcare workers, and each patient requires half an hour to be seen, or half a day to be seen, then I'll have to wait half a day to be seen. Okay? So that's the idea. Yes, question?
Sorry, so it's like infected divided by healthcare workers or staff time times infected divided by healthcare?
It's actually, either one turns out to be the same mathematically, but in my original version I actually had, it's probably, you could think of it either way, but I actually do prefer to say, okay, it's more like this. Sorry. It's more like this. Okay. like that. That's the way I kind of prefer to think about it, in the sense of I've got this many hours of treatment that have to be conferred by the healthcare workers overall, that it has to go around among this many healthcare workers. So I kind of prefer to think of it like that. Does that make sense? Yeah. Okay. Okay, other questions on this? Do people want this up on the board more? Yeah. You're looking for help? Okay.
Oh, something happened here. See, there's a cloud there.
Did it get disconnected, Kurt?
Yeah,
Green is the color.
green is the color.
Okay. Okay. Okay, ladies and gentlemen, are you ready to run it? You ready to run it?
What did you have recovered in immune set?
Recovered and immune.
Yeah.
This was set initially to 0. And after that, it just depends on the flows. Okay, who would like me to show something else
Can you click on recovery delay?
with the light? That's this guy here.
Yeah, we just need to have, just need to have a link. Links. It's actually helpful. And then you can see what's.
What depends on what? Okay.
All of these are just like link things. They're not. So it's saying here the issue is saying recovered is used. So that's being used, but it's not being expected.
I have that too.
Recovered and used.
Oh, it's being used but not expected?
Yeah, it's recovered.
Okay, if it's being used but not expected, there's a missing arrow,
Right, so there should
a missing
be
link.
from here to here. There should be another arrow.
So in other words, you'll get that if, for example, there's a missing link here. It's the missing link. What's that?
Oh, I
Oh, okay. Yeah.
There's an arrow from here.
Okay.
Yeah.
that diagonal one.
Oh. Oh, okay, yeah, this guy.
here is the normal. Each one
Yeah.
of these has one, right? From the stock.
I think it may still work even if it complains to the link. It's
It
just
will still work. Yeah.
it's truculent. It's unhappy, and it's yeah.
Yeah, because it's breaking. That's how the system dynamics models are developed.
Yeah.
So
They're
it's
standard.
seeing that I built a formula, but I didn't put the right links in, or vice versa.
Right. And in general, it's considered really good practice to have in place links that indicate what depends on what. And so if there's a dependency on a variable that's not shown with a link, it's considered, it's kind of misleading because you have this model, this depends on that, but it's not shown. And so you want to be able to look at the model and say, okay, what depends on what from a high level? And if I want to see in more detail, I can go down to the formulas. But a lot of the time, if I'm working with stakeholders, they don't want to see all the vague details of exactly how it depends. What they want to see is, oh, wait a minute, this one doesn't depend on that. It needs to, because this is an important factor for it. That's the high-level insight that they'll often bring to bear. And this is kind of a way of balancing not wanting to give too much information, like forcing them to look at all the formulas, but not wanting to give too little. You want to have it be fairly transparent about what you're assuming, or at least in rough terms what you're assuming, but not provide so much information it's overwhelming to non-technical folks. Yeah. Okay. So, ladies and gentlemen, shall we run this model? Who needs deployment of green? Okay. Okay.
Could you just click on one thing for me?
Sure.
On infective.
Infective. This guy here?
Yeah.
Yeah, it's initially 470. Yep. Are you ready to roll? Are people ready? Wow. I take it that was of the model and not of me.
I think you better that.
Okay, well, I won't object. Okay. Okay, that's great. Okay, so now what's going on, folks? What's happening? Okay. So, okay, some things are kind of obscure here because it's getting cut off. Let's remedy that so you can see it more clearly. we're reaching kind of the final zone of this, and I want the points to be clear. So what I'm going to do is I'm going to leave more room here at the edge, so it will show numbers that are large without truncating them. Hey, come on, get over there. Boom. There we go. Okay, so let's run this. Let's run this thing. Boom. And here we go. Boom. Okay. So what's going on? Narrative-wise, what's happening? This is infectives down here, and this is all three stocks up here. We used to have to create our own little graph of this because it was so small we couldn't really see it. Is that still the case? No. Number of infectives is it high or low? It's very high, right? If you click on this, it'll highlight it for you. There it is. It's this one here. Susceptibles is this one. Recovereds is this one, right? Okay. You can, by the way, you can click on it again to unhighlight it. Okay, ladies and gentlemen. So this is very high. Why is it high? Why is that going so high?
Because of the recovery.
Okay, so let's go see what the recovery delay is associated with it. Okay, the recovery delay is, oh my gosh, it's about 10 years or so, or 9 years. Okay, that's a long time to wait if you have gonorrhea. So if you have a treatment-mediated infection, the point is that that's preventing people from getting treatment for an awful long time. Okay, so what can we do to improve the situation, ladies and gentlemen?
Add healthcare workers.
Add healthcare workers, yeah. I didn't get called by the mayor of St. Louis for this one, but it is something that we have to ask. What do? We have to add healthcare workers. Okay, so ladies and gentlemen, let's go do this. What do you think? Let's go add some healthcare workers, okay? So what I'd like you to do is do it this way, okay? Let's go, and I want you to do this carefully, because we're going to compare it in two ways. I'd like you to go like this. I'd like you to go back to the main screen you can either close it and rerun it, or you can press the big red button here and go back. And then I'd like you to press this button, step. Okay, that's going to start the model running. Just go to the beginning of the model, and then I press the button to go see it. Okay, now I'm at the very beginning of the model, and I'm actually going to run this out just a little bit. I'm going to start it running, and I'm going to pause it after about, let's say, 100 days. So I can speed it up with this. It's just showing it nice and slow for my sake. And I'm letting things take off. You notice that what's going on during this time. Can you see it? Can you see what's going on? Okay, it's going really high. Okay, I'm stopping at about 100 days. And now I'm going to add some healthcare workers. So here's my question for you. How big does the number of healthcare workers have to be to control the infection here? So let's go and set it to, what do you think? Anyone? Okay, let's set it to 100. Okay, good. Okay, I've now updated it to 100. I'm going to run it forward. Okay. Oh, look, it's starting to go down, right? Okay, that's a good sign. Started to go down, yeah. Okay. Let's speed it up even more. Okay. Did that control it entirely? No, it brought it down some, but it didn't bring it down enough. Okay, let's go do this again. Let's run it out to oops. Let's go restart this again, and I'm going to slow it down a little bit here, and I'm going to run it out to about time here, about at time 100. Okay. Anyone else want to hazard a guess? Maybe not 100. How many? How many? Okay, 175. That sounds like an informed guess. Great. Okay, so now let's run it out here. Okay? Now we're seeing some real progress. But no cigar. It's brought it down by a factor of almost 2. And maybe eventually, but it seems to have plateaued at this new sort of phase. Okay, ladies and gentlemen, we can play around some more, but I will tell you by playing around that you're going to actually need a considerably larger unit yet.
623.
Okay, I think the eyes have it. So let's try 250. Okay, try 250, and 250 we certainly are having more luck there, but it is still not quite doing the job. We're able to sort of work through a lot of the backlog. The recovery delay is lower, but it's still not to the level that we're able to treat those cases soon. Now, if we could treat it, say, with 300, okay, oops, hey, 300 here. Okay, let's try running that. Here we go. Okay, now we're getting to the point where the recovery delay is getting very small, and you notice there's kind of this tipping point where, boom, it remarkably sort of decreases the number of immune people, and you get this real breakthrough. Okay, so that's great. Ladies and gentlemen, let's go take a look at one other strategy, and then we're going to reflect on the day. Okay, so ladies and gentlemen, I'd like you to take this, and I'd like you to actually copy it, and I'd like you to paste it. Okay? Okay? So I didn't do that quite well. Copy, and then go click on the whole model and say paste. That's just so we can copy the settings with it involving time that we said earlier. And now, ladies and gentlemen, I'd like you to set the number of healthcare workers here to successively larger values. And I want you to tell me the number that are needed to break the cycle. These are number of healthcare workers we have from the start. From the start, not from later on, but from the start. Okay, so going through this, let's do it. So let's try to find the number of healthcare workers. You could try it with 40. We could do another one. Let's call it, simulation. I'll say 40 HCW. Yeah. And now let's do it with another one, which would be here 50 HCW. And I'd like you to find the sweet spot where it actually is successful in controlling the infection. So I'm just I'm pasting each of these in, and I'm going to say 50 HCW healthcare workers, and go set 50 here. And you can do it. I would actually do it as every 20. So I'll say 60 actually for this guy. Okay? So how many healthcare workers do we need up front? Anyone? You can do the experiments. Does 40 do it? What happens with 40? 40, does it do it? Is it successful? Okay, how about 60? This is 60. Is this successful? No? How about 80? Anyone? Let's try 80. Okay. Okay, we're going to
Drops it really before it starts.
That's exactly right. Okay, so let's try it. Basically, it never takes off. Exactly what was said. What's going on here, folks? How is it that before we seem to require what, 300? But here we can do it with 80. What's happening?
There's not that many infected yet, and so they have enough healthcare workers to quickly go through.
That's right.
Treated.
So what we're seeing here, folks, is an aspect of lock-in and path dependence. So when we run this with different numbers of healthcare workers, we'll see very different trajectories. We'll see different trajectories. Larger number will bring it lower, but we're still sticking with basically fighting this endemic infection up to about 300 after the fact. But if we have those healthcare workers up front, we can get in a situation where we can fly ahead of the plane. We can avoid the infection exploding in the first place. Therefore, we can keep the treatment times down. Therefore, we need fewer healthcare workers to treat the patient volume to keep it under control. In short, ladies and gentlemen, if we allow the outbreak to take off, to reach high levels, we're dealing with a mop-up situation or a remedial situation that requires a huge amount of resources to bring under control. But if we invest a small bit of resources up front, we can head it off. We don't get locked into this endemic situation, which burdens us with very high volumes of patients and therefore very high needs for resources. So if there's one lesson from this particular iteration of the model, it's a sort of a stitch in time saves nine. Investing those resources up front rather than bringing them to the table only later can have a huge benefit in terms of controlling costs. If you can prevent a situation from spiraling out of control, it can be a lot cheaper, a lot less time consuming, a lot less risky than by trying to respond to it after the fact. It's kind of like responding to a fire after it's been set versus preventing fires. So here we have a model that you've built up that illustrates this important principle of lock-in that we see in many systems. This is a phenomenon we see in dementia wards. You know, if you have a really good experienced nurse that can sense patients' agitation, they can head off whole sets of problems that otherwise would throw the ward into turmoil, where one patient starts acting up, it ends up rippling over to the agitation level of other patients, and suddenly you're dealing with fighting 20 fires. Whereas if you can head that problem off from the start, you can make do with far less in the way of resources. It's like that also with nosocomial infection in long-term care facilities or hospitals. If you can't fly ahead of the plane, you're ending up putting a huge amount of effort in for cleaning, for disinfection, for locking down wards. You may have to block visitors from coming in. But if you can keep the situation under control by enough investment of resources early on, if you can reach that sweet tipping point, then you're going to be in a situation that's much more favorable, both in terms of effort expended, in terms of costs, and in terms of often health outcomes. So this is a model which demonstrates this characteristic of path dependence and this characteristic of lock-in that we see in a pronounced way in a lot of systems. Now, this particular model, like many of our models, has been further investigated with more detailed models. Often we use these system dynamics models to investigate upfront quickly. In an afternoon, you can build up a model. put in some rough data, explore, get some sense of the dynamics, get some appreciation for where certain patterns are coming from, and then you might investigate further, say with an agent-based model, to investigate not so much where to intervene, but how to intervene in detail, or to test the robustness of the conclusions to which it was very sensitive to particular specifics. And in this case, as in several others, when we've tested our strategies from a system dynamics model with a much more detailed agent-based model, we found generally consistent patterns, but some additional insights that can come through the development of the agent-based model after a period often of many months that it takes to develop, a suitably rigorous model. So while this is just a small example, it's one that does illustrate many of the features of complex systems. It gives you a bit of a taste as to what it's like to build a model within these tools that we've been dealing with. But it also highlights, I hope, some features within the system dynamics, but system dynamics trade-offs that that may be useful to reflect on. So some key take-home messages from this. So I emphasized early on today that models express dynamic hypotheses about processes underlying observed behavior. This is true for any of the dynamic modeling types we're talking about this week. System dynamics, agent-based modeling, we'll see a little bit of a glimpse of discrete event modeling in a hybrid context tomorrow. But fundamentally, we're seeking to reason about the causal structure of a system, or to posit for an exploratory purpose a certain causal structure and see the degree to which it might explain phenomena or patterns that we observe empirically. And these models help understand how diverse pieces of the system work together, how theory about one area of the system have implications for the broader system or for more distal outcomes. System dynamics in particular focuses on feedbacks and accumulations as shapers of behavior. And I tried to weave into my narrative, folks, some descriptions associated with those phenomena as we were building up the model. Indeed, when we were trying to explain these patterns that we see in the simulation in the context of these outcomes, both before and after we had the simulation of healthcare workers, we could appeal to the feedbacks involved. We could appeal to the very rapid change here being associated with a vicious cycle. The more infectives, the more infections take place, the more infectives. We could also explain the dips and valleys associated with those fluctuations, those oscillations, which we see in real epidemiological time series, say for childhood infectious diseases, which are now starting to reemerge. And we can explain them in terms of negative feedbacks and in terms of delays. Stocks and flows are very powerful mechanisms for understanding dynamics, even in contexts where you don't use them to characterize dynamics from the start. But more than that, ladies and gentlemen, we also saw that accumulations, in addition to feedbacks, were fundamentally useful for understanding some of those dynamics and the oscillations and delays. All these models are specific to purpose. They abstract away from a lot of detail like any map, and they help us focus on the salient detail for our needs, to address our questions. But unlike maps, it's often harder to figure out up front what details are needed for sure. There's a lot of exploration and learning that goes on because we're working with nonlinear systems where the behavior of the whole is different than the sum of the behavior of the parts, and where often we're surprised by the level of influence certain pieces have. So we have to be a bit cautious about presupposing that one thing is not important or another thing, and there's a lot of experimentation that goes on. One thing I tried to emphasize a lot in the morning was something I thought fairly distinctive about system dynamics, which is its traditional depth of emphasis on both the qualitative and quantitative components. these are components that do allow from the very first meeting, like that meeting with that rural village in India that we saw from Peter Hoffman's photos. It can allow some insights to arise, some elicitation of understanding from stakeholders that wouldn't otherwise have been incorporated into the model. And that's very powerful. But those qualitative models also provide a home for more qualitative features of a situation. Features of a situation that are softer in character, perhaps involving aspects of stress and fatigue and burnout, and aspects associated with very real human matters, but which we may lack sufficient data to put them right now into our quantitative models. But they can provide a home for sort of sketching out theory from a community, for example, perspective or other stakeholders that's inclusive and that dignifies those components even if they're not yet into quantitative models, but puts them in our list of things to consider in adding to the models. And system dynamics models do admit, although I didn't emphasize it here, to formal analysis and reasoning that can be profoundly powerful. One of the things I find most promising in this area is in the domain of big data, of going beyond this sort of dichotomy where we build the model first and then we use it for insight. We build it, we use it, and then over time we update it, but only occasionally. Increasingly, when we have this recourse to data coming in over time, which is increasingly available about everything from physical activity patterns to people's location, contact patterns, people's reports of risk perception, etc. We have a situation which is increasingly amenable to ongoing incorporation of data into models in a seamless way. And this is an area where system dynamics really can shine for some technical reasons that we don't have time to go into in detail. The analogy that I'd like to make here for my students is that even the most refined mental model is one that has to be checked on an ongoing basis with empirical observations. So, if we go to our workplace and we seek to go home, most of us have an extremely refined mental model of how to get home from our workplace. But we would never think to do it in a way that was without further observations. We'd never think to do it with our eyes closed. It would be a recipe for disaster. It would be a fool's errand. We'd try to go home and we'd get hit by a car, we'd misjudge where the curb is, and we'd break our foot, we'd fall into a manhole, whatever. We'd end up in all sorts of grief if we tried to get home with our eyes shut. We have an exceptionally detailed mental model, but it's going to miss some features. And even if we have the most detailed computational assistance to sort of guide us, the Google Maps to give us directions, it's not going to know about whether the lights are green or red, whether the walk signal is on. So, when we're trying to navigate in the world, we do so with constant recourse to observation. And we within our models, I think there's a similar need for constant recourse to observation. And the question here is, why do we base projections and planning with our models on blind models that are only updated occasionally? So increasingly, what we're seeking to do is to take models that may be built very quickly in response to an emergent need and to combine them automatically with data that's incoming on an ongoing way. So the idea here is we're not going to just rely on the model's anticipation of what the current situation is, but we're going to be incorporating into it the very latest evidence. It's kept current with the latest evidence. And it turns out that, that system dynamics models are very amenable to this through tools of machine learning called particle filtering, Kalman filtering, and techniques within the predictor-corrector rubric more generally. So the idea here is we can have a model that's terribly, terribly off, but it gets regrounded periodically when data comes in. It sort of corrects its interpretation of the current situation, and we can use it to plan forward. And in the best of contexts, we can have a model like this learn over time from observations to refine its parameter values and refine its anticipation of what's going on. So here we're sort of balancing the fact that we are uncertain about the model, uncertain about the data, and combining them together into a consensus estimate in the form of probability distribution that's very powerful. So a few other sort of key take-home messages. One is in terms of strengths of system dynamics. I mentioned some this morning, and I want to reiterate over them. One is we can capture with these models very rich dynamics associated with continuous variables. The theories I've mentioned at a physiological level of Guyton and others. We can have models that characterize immune system function, but also models that seek to characterize psychological factors, such as the impact of work pressure on error rates, such as have long been contributed within the system dynamics area. A second real great feature of them is rapid model prototyping. If someone like Kurt, myself, or others is faced with a new problem, often we'll throw down a system dynamics model very quickly. And it can be assembled often at a very rapid level with very little in the way of any sort of programming, as you've seen. You've all built up this model. And you can use that sort of model to probe at a beginning level sort of what might be going on in terms of the high-level processes. Another real key feature of it is its excellent support because of causal loop diagrams and honed processes that have been well contributed to the literature for participatory modeling. There's a resource called the Scriptopedia, which seeks to provide guidance for participatory modeling projects using time-honored sort of types of exercises to work with stakeholders, and a really well-developed qualitative mapping tradition that can be understood almost immediately by stakeholders in the form of causal loop diagrams. The capacity for interactive simulation in the later phases of the project, because of the quick response time of models, is also very attractive for many types of interaction. As you've seen, the models are not trivial to build. It should take some stretching of yourselves, and I'm well aware of that. But the fact that you're going away with a built model is a testament to the fact that there's less dependence here on deep computational skills. You can actually build up a model that's reasonably rich and reasonably insightful without a background in computer programming. Now, being someone who teaches software engineering, that's not a big constraint for my computer science students, but it's a huge constraint for my health science students who come to me and seek to contribute with models. And system dynamics models are well within the tool set that they can wield with confidence after just a semester worth of training. With formal analysis, we didn't really go into this, but it turns out that using that model, for example, that we built together, I have some very detailed results that demonstrate the possible behaviors of those models over a wide variety of possible parameter values that help us understand why we're seeing those patterns and help us understand in what cases those patterns might radically change based on the values of parameters. And what that can mean is that you could take the learning from a given model and without exhaustively running the model, translate that learning to a different context, a different pathogen, a different situation where the constraints are different, the availability of resources is different. So with formal analysis, we can gain some quite deep insights about models. But at the level of regular tools, they can also give you really powerful ways of integrating it with incoming data, as we talked about briefly. But further, ladies and gentlemen, they can help you highlight sort of which areas of the model are currently dominant in shaping the model behavior. They can help you better understand what's driving the patterns that you've seen. And finally, they do serve as a very natural vehicle as boundary objects with stakeholders from diverse backgrounds and in the context of cross-disciplinary teams. Okay, I think that's all I have time to give and all we have time to cover today on system dynamics. There's plenty of other things in the slides that I did share, including some on formal methods, including some on sources of data, including some on calibration that I'm not going to be able to cover here. They may be the sort of things that in the next 2 days we might be able to make some basic comments on if there were a strong need to do so. But any closing questions or comments that people would like to make before we finish up for the day? Yes.
You mentioned a set of resources around participatory
Yeah.
modeling. What did you call them? What are
Well,
they?
there's a thing called the Scriptopedia. This is a resource that's maintained by George Richardson and Peter Hoffman. Peter is, I think, the main driver computationally behind it. I believe it's located at Washington University in St. Louis, physically. But what it contains is a wide variety of scripts that have been used over the past 2 decades, I think, in engaging with models with stakeholders. So sort of, when I say scripts, what I mean is kind of exercises that they've run about how do you approach non-technical stakeholders to elicit from them most effectively their perceptions of a system, to understand from sort of certain, as we call them, reference modes that they might be thinking about behavior over time that they may have encountered. And I think it contains a couple dozen scripts that people have used in different encounters and comments on how to run those scripts effectively in a group model building exercise so that they run in a defined time with appropriate, findings, to make sure that power differentials within the group are respected. So if you have people who are deputy medical health officers together with nurses, that the nurses will feel comfortable speaking up and won't be overshadowed. Very practical stuff when you work with groups to understand the political sort of sphere. And that's the sort of work that they've been doing for decades now. It's George Richardson's group, and the chap is David Anderson, who really takes the lead of it at SUNY Albany, and then with Peter Hoffman at Washington University in St. Louis. There's also folks in Nijmegen who have a book on this, a group model building book by Jack Venix, Vennix, which is really a very nice reference in this field. Peter Hoffman recently came out with a book as well, which includes a significant component on participatory modeling in health, and I'd recommend that wholeheartedly. I see him as the world leader in this particular area, although George has also done some very good work. So,
Thanks.
yeah. Other questions?
2 quick announcements. One, apparently this room is not actually supposed to be available, and we're not supposed to be here, and we definitely cannot be here tomorrow or Friday. So tomorrow and Friday we will be in SPH1, room 2615, which I've written up on the board there. If you go up the staircases when you come in the lobby, it's on the right-hand side as you exit the front doors.
Okay.
And it's pretty easy to find. So we can do that.
Great. Is that something Matt has sent out, posted a notice on C-Tools?
Yeah.
Okay, great.
I just want to make sure that, and secondly, I just want to make sure that everyone knows what group they're in and has the right contact information for everyone else in their group. If not, we should spend a couple minutes coordinating. The plan is to spend all afternoon. Tomorrow morning, we're going to do some special topics. We're going to talk about hybrid models, use of models for policy, we're going to answer unanswered questions, and then in the afternoon, there's going to be a lot of intensive work with your groups and on your individual projects. So I'm sure everybody's thinking about those projects and things to get the most possible out of that session.
And in that session, Ross and I and the TAs will be available and circulating so we can introduce those groups.
Wait, sorry, just to clarify. So the time tomorrow is to work on our projects together, like our presentation together?
So
Or should we come with, like, already having done some on our own projects?
So Russ, do you want to comment on that? Or do you
Yeah, I
want me
mean,
to?
we'll see how far you get. I think ideally you would have made some progress on an individual project by tomorrow afternoon in any case, since we'll be presenting it 24 hours later. And the more progress you make, the better job you can do of getting initial feedback within your small group and doing some comparing. I think we didn't completely decide on that, but I would guess that you would aim for between 10 and 12 minutes per person, with an additional 10 minutes of group per group of group compare and contrast, and then we'll allow something like 10 or 15 minutes per group of questions or feedback.
And so we're talking about concepts
Yeah, you missed that part when you got here, but it's good for everyone else to hear. The idea of your projects is that you're going to propose a specific question, you're going to provide background on the topic that we really need to know to appreciate why a particular systems modeling technique that you've chosen is well suited to that topic, and you'll make a case for that. Then you'll outline in broad strokes what your model will consist of. So if it's an agent-based model that you've chosen, you'll say in broad strokes what the P, the A, the R, the T, and the E might be. If it's a system dynamics model, I would imagine you would expect to see some indication of what the key causal variables might be, what things might be stops or flows, and what kind of outcomes you might be.
That's right. Possibly causal loop diagrams, exogenous, endogenous, ignored.
Yep.
Yeah.
And then at the end, you might spend a little bit of time in your paper talking about what data challenges you might expect to encounter, and how you might deal with them. And then in groups, the idea is that you'll compare and contrast within the group the similarities and differences that you go through experiences of trying to do this and the models you expect out. Any other questions about the projects or the plan for tomorrow, or where to go? There is a keynote lecture by a visiting professor who is actually the chair of the department that he was in at USC, and John Samet, across the hall in SPH in the main auditorium in 5 minutes, and you're welcome to attend it. They have one every week at GSF.
Great. It's in the other building,
In the other building.
which you can get to. It was raining cats and dogs last time I checked, so
It stopped.
it stopped. Great.
Welcome.
John, what is that, Kurt? Jonathan Salmon. I think it's how epidemiology has contributed to positive health outcomes and will continue to do so. Something along those lines. Yeah.
Someone told me that the job that has had the most impact on human life is engineers.
Yeah. I did hear that. Yeah.
True, man. I'd say plumbers.
Yeah, they were talking about like sanitation and basic sort of outcomes to provide shelter and sort of safe
Yeah, the
conditions.
basics, like the super basic.
Yeah.
Although I might go back and say farmers.
Yeah, right. Darn right.
Mothers.
Yeah.
Did you say that's right? I know that's right. That's totally right.
It's
I didn't
true.
see anybody leap up and say that they didn't know who their group was or didn't have contact information. So okay,